welcome to all of you to this virtual dissertation defense of Romulo Miragoes. And it's a pleasure to see so many people, 45, and you all witnessed 10 minutes of frantic activity here trying to get the committee members to Zoom into the meeting. As I joke, we have this issue of additional security per RACAM guidelines, but the topic is about cybersecurity or related to cybersecurity, so this is timely. So I think I will not use any more of the time here. Romulo will make a presentation of about 40-45 minutes. Committee members, of course, are welcome to ask questions during the presentations. Then the questions would be open to the general public first in the public part, then to the committee members, and then the public Zoom session will go on hold. The committee members will go into a private meeting with the candidate, and then that'll be the end of the process. So, Romulo, would you please start? And I'll ask everyone to mute themselves, and I will monitor the chat box for. Okay. But of course, the committee members, please, at any time, you can just unmute and interrupt. No problems. Thank you. All right. Thank you all for being present today.
All right, thank you, Stefan. Yeah, I'm excited to present a high level and small part of my dissertation today. And one of the perks of presenting over Zoom is that my family, friends, and colleagues that are far apart are able to show some support today. So thank you. I like to start this presentation with the general context of cyber-physical systems, which are an important class of systems in our society. So in the bottom, I have illustrations of examples of cyber-physical systems. So power plants, autonomous vehicle, medical devices, those are examples of cyber-physical systems. And these systems are defined broadly as the integration between a physical process, a network system, and a computational unit. And I like to portray them in this feedback manner or feedback control loop manner, since my background is controls, where the sensors are collecting some information from the physical process sent to the computational unit. And on the other hand, the computational unit is going to control the physical process via the actuators. So what motivates my dissertation is that these systems are vulnerable against cyber attacks. So my dissertation is going to be focusing on investigating security problems in the cyber layer of cyber-physical systems. And to be more specific, my work pays attention on sensors that are vulnerable, subject to be compromised by an attacker. And these are known as sensor deception attacks, where the attacker is trying to exploit some vulnerabilities of the computational unit in order to cause damage to the physical process. So we will in particular focus on two viewpoints. So the first one is how can an attacker cause damage to a given cyber-physical system? So here the attacker is trying to exploit the cyber part in order to cause this damage. And how can we improve resilience against such attacks at this higher level layer? In the bottom, I have a few examples that show these two viewpoints. So in the first example, I have a robot in a grid where we can synthesize an attacker that is going to create a mismatch between the correct robot position and the position where the controller thinks the robot is. And by creating this mismatch, now the robot will crash into the red barrier here, and so the robot is unsafe. Similarly, in the second video in the center, again, it's about synthesizing a sensor attack for a controller that regulates both the temperature of a room and a heater. So again, we're able to synthesize an attacker that will create a violation of safety for this system. And I'll come back later to this example. And in the last video on the right, I demonstrate a controller for a robot in a grid that is actually robust against sensor attacks. And I'll come back to this example later on the presentation as well. So in order to answer these questions, we need to formally characterize sensor attacks in cyber-physical systems. So we start with the CPS, the cyber physical system, without attack. And we have a way to define its control behavior. And there's a clear separation here between an unsafe region and what is the control behavior. So we assume that we start with a safe cyber physical system. Now, when we bring the attacker into the picture, we must be able to characterize the closed loop behavior under attack. And this characterization must be general, such that for different attack strategies, we are able to define these attack behavior. And this is actually what my dissertation tackles. We want to define a general framework of sensor deception attacks in cyber physical systems. So the outline of my presentation today is defined in this slide. So I first present how we characterize cyber physical systems under sensor deception attacks. And then once we clarify this first step, we can move on in answering the two questions that I have mentioned before. So first, we go into the offense, and we're going to exploit vulnerabilities of a given cyber physical system. Then we go to the defense side and investigate how can we make this cyber physical system robust against sensor attacks. So the idea for today is to give a high-level overview of my dissertation, and I will only cover parts of my dissertation. All right, so before we move on into what I actually have worked on, I need to review some concepts so that everyone is in a similar page. So we'll be assuming that the CPS is abstracted and given to us as a discrete transition system. And I'll be using this simple example of a road intersection with two cars to demonstrate some intuition about the methodology and the methods that we developed. So by discrete transition system, I say that the system, the CPS, is given to us, is modeled as a deterministic finite automaton, where we have a finite set of states, a finite set of events. So for example, event B int represents the blue car entering the intersection. And we have a transition function that shows how the system dynamically evolves. And finally, we have also an initial state. So this DFA generates a language, which is the possible concatenation of events that can be generated by G. And this represents the behavior that can be generated by the cyber physical system. And we use this notation in this slide to formally capture these definitions. All right, so we assume that our model here, the DFA that is given to us, is capturing all the behavior that the physical process is capable of generate. So next, we would like to guarantee that nothing bad happens to the CPS. And this is where supervisory control theory is going to help us. So we're going to first assume that the given plant has a finite set of critical states. In the intersection example, this will be the state 5 here, where the two cars are in the intersection at the same time. And then a supervisor acts upon this plant by observing the events generated by the plant, and then it disables some of these events in order to the plant, so that the plant does not reach the critical state. And the supervisor is actually different from the usual controller, because the supervisor does not tell the plant which events it must execute next, but it tells which events the plant should not execute. And after that, the plant will decide how to proceed. So we can model in this framework, we can model limited actuation capabilities by partitioning our set of events into controllable and uncontrollable events, where the supervisor only disables, should never disable uncontrollable events. And we can also model limited sensing capabilities, where we have now partitioning the set of events into observable and unobservable events. And the supervisor only sees observable events. In my talk, I'll be focusing only on the full observation case, or most of the time in the full observation case, even though my dissertation does cover the partial observation as well. So in fact, we can actually assume that this supervisor is also encoded or modeled as a deterministic finite automaton. And we use this notation here where supervisor S is supervising the system G. So this will be our controlled system, and it generates a language as well. In the intersection example, the supervisor is going to act as if two stop signs are added in the road. So the first car that enters the intersection is going to have priority over it. And the second car can only enter the intersection after the first car exits the intersection. Okay, so just for completeness, so the supervisory control theory was introduced by Ramage and Wohan in the 80s, and it's quite comprehensive now. There are properties for sufficient and necessary conditions for the existence of a solution, and these are the controllability and the observability properties. And there is effective ways of computing the supervisor, and this is done through fixed point characterization on languages. And in this talk, in my dissertation, we use these three characterizations here. So for example, the supremo controllable sublanguage. And here supremo means that we are looking for a supervisor that only interacts with the plant when it's necessary. And this is, the supervisor is minimally intrusive. So only interacts with the plant when there will be a violation of when the plant's going to reach a critical state, for example. Okay, so that was it for the review part. I know that was quite brief, but I just want to give some intuition about the supervisory control framework. And because the idea now is that my work is going to be building upon this supervisory control framework, where we're going to be introducing an attacker into this framework. So is there any question or any clarification at this point that I can talk about this three first slides related to the review? If there's no question, then I'll move on to the work that I have done. All right, I think I am on the clear. So the first step, as I said, is we are going to introduce the attacker into the supervisory control framework. When we do that, we're going to introduce the attacker in the communication channel between the plant and the supervisor. And there are a few assumptions that we're going to make about the attacker. So first, we assume that the attacker observes as much as the supervisor, and he hijacks a subset of these sensors. So by hijacking, I mean that it can insert some fictitious event in the channel, or it can delete legitimate events from this channel. We're going to be using this notation here to denote, for example, what are the events that are compromised that can be hijacked. So sigma sen denotes those, will denote these events. And we use this notation for insertion and deletion. So we want to have this notation here because we want to be able to differentiate what is the actions, differentiate the actions of the attacker from the events that are executed by the plant. And we want to do that because our idea is to actually enhance the plant and the supervisor model with attack action. So we are going to include new transition in these models so that those transitions are going to simulate the insertion and deletion that the attacker can do in this channel. And this idea comes from Carvalho and Lima. So the attacker, as I said, can insert events. So we are going to add additional transitions into the plant model and the supervisor model that are going to represent or simulate insertions. Here we are assuming that we're using the intersection example where the compromised event is just our int. So this is the red car entering the intersection. And we do the same for deletion events. So we're going to have additional transitions that are going to simulate deletions into the plant and as well in the supervisor. So if we move on to our example, we can compute now the models, the enhanced models for the supervisor and the attacked plant for our example. So here the new transitions are in orange in both of these models. And just to differentiate, we're going to call these models the attacked plant and the attacked supervisor. But if you think about it, I didn't introduce, or I never talked about attack strategies, right? I just said that I'm including every possible action that the attacker can do in this channel into the models of the plant and the supervisor. But at the beginning, I said that I want to have a general framework where different attack strategies, where I can characterize different attack strategies as well. But in fact, it becomes easy to introduce these attack strategies now because the attacked plant contains all possible attack actions. So now we can introduce this attacker as acting as a filter. So where it's going to filter some of the decisions that we included in the plant. And we can do that by assuming that the attacker is given to us as an automaton, and then we can compose the attack strategy with the attacked plant so that this filter is going to happen. And we use this parallel composition to do this composition between the attacked plant and the attack strategy. So here I have one example, which is called the all-out attack strategy. And there's no filtering happening at all at this example because we can see that the attacker is letting every event to is still able to execute. So this will be kind of a worst case attack scenario that we have. So the attacker can do everything that is possible. But we could have different attack strategies. So now I have a bounded attack strategy where the attacker is bounded by 2 insertions. So the attacker can only or can insert at most 2 events. Then it needs to wait for the system to execute an event in order to insert again. So this will be a bounded attack strategy. So I'm not going to go into the details, but there are other works that investigated different models than ours. Some of them are going to be focusing in specific attack strategies, so just modeling bounded attack strategies or just some different attack strategy. And I also want to actually thank Dr. Jana here because there was a mistake in our formal, our general definition of a attack strategy that we were able to fix as well. I'm not presenting here the general formulation of our attack strategy, but there is a behind this automaton encoding or this attacker strategy as an automaton, we have a general formulation as well. So I appreciate his comments. All right, so now we have all the pieces that we need in order to define our system under attack. So we have the attacked plant, the attacker, and the attacked supervisor. So this is going to define our system under attack. So the attack supervisor is supervising the attacked plant composed with our attack strategy. And from this system, we can actually extract 3 different languages that are going to be quite important for our problem formulation in the next in my presentation here. So we can extract the first language that we extract is the augmented controlled attack language, where in this language, we still can differentiate what is the attacker action. So we can see what is an insertion, what is a deletion, and when the attacker does those. And we have also the language that we call the executed by the plant language, where we have this projector operator that is going to project the attack actions into how the original plant executes them. And the same for the observed by the supervisor language. So again, we have a projector operator here that is projecting the attack actions to how the supervisor sees them. And this can be formally defined by these formulas here, where, for example, for the projection of based on the plant, an insertion is a fictitious event. So the plant does not execute any event at all at this point. So when we're projecting it, it's going to be projected to the empty string that we denote by epsilon. While a deletion, that's going to be an event that was executed by the plant, but the attacker deleted. So the projection of a deletion is going to be the legitimate event itself. And the same here for the supervisor projection. So actually, that is it. So we have a formal way of characterizing the framework of supervisory control under sensor deception attacks. And given the original framework and a attack strategy, we can characterize this control system. So with this characterization, we can actually move forward to address the two questions I discussed in the beginning of my presentation.
Can I ask a quick clarification?
Yeah. So that's actually a good point. Yeah.
So how should I think about the order of play? I feel like deletion is synchronized with the plant, but insertions, can they be asynchronous in general?
So in our formal, like our general framework, the insertions, they're always going to be triggered by something that the plant executes. So that's how the attacker is going to have its strategy. So if something new is executed by the plant, then the attacker will can insert at that point. So that's how we see. And it can insert, normally has a strategy, and here there will be maybe some assumptions that we have how much the attacker can insert before something else happens in the plant. So that was the idea of bounded, let's say bounded attack strategies. So if we bounded by, let's say 2 events, so then we can assume that the system will not execute anything in between. So then the attacker can insert those 2 events. So that's how we synchronize the insertions. Does that answer your question? Yeah.
Thank you.
Okay. Any other questions here before I can move on to the offense side and go to one of the 2 questions that I posed at the beginning? Okay, so to remind you all, so the first question that I posed at the beginning was that we want to exploit vulnerabilities of a given CPS. And namely here, we want to synthesize a sensor deception attack strategy. So when we were defining the system under attack, we assumed that all the pieces that were involved, the plant, the attacker, and the supervisor, these were given. So now actually we are searching for an attacker, but not any attacker. So we search for one that causes damage to the plant, but stealthily. And here, what do I mean by stealthily is that there exists an intrusion detection mechanism that is trying to identify any inconsistency in this control system. And the attacker does not want to trigger this detection mechanism. So that's the intuition of the problem that we're trying to investigate. So again, to reinforce some of the assumptions of the attacker, so we have that the attacker observes as much as the supervisor. Again, it hijacks a subset of the sensors, and we have this extra assumption that we say that the attacker knows the plant of the model, the models of the plant and the supervisor. And this is a strong assumption, but we're looking for the worst case scenario. So could we synthesize an attacker even if it knows the model of the system? So again, I'll briefly mention that there are researchers trying to answer this question as well. So normally they are looking into specific attack strategies, and we have, so for example, only looking for bounded attack strategies under these constraints. We are searching for a more general problem formulation, as well as where we can have attack constraints added later in our process. And there's also some people that investigate intrusion detection problems, but these are different since they're trying to they search for better intrusion detection mechanisms and what are the guarantees that these mechanisms provide to the system. Okay, so intuitively, we search for an attacker that generates a behavior that intersects with the unsafe region. And we can define the attacker stealthiness based on the control behavior without attack. And this will be the region in green. So if a supervisor always observes behavior in the green region, then it does not seem suspicious that there is an attacker in place. And that's exactly the constraints that we have to our problem statement. So we want to synthesize a sensor deception attack such that first, the attacker is complete, meaning he always knows what to do next. The second constraint here is the supervisor observes the controlled behavior without attack. So this is the stealthiness. And the damage part is that the plant executes unsafe behavior. We can present these three constraints more formally. I'm not going to go into the details, but note that we do use the three languages that we defined before. So this is the augmented language. Here we have the supervisor language, and here the plant language. So that is the problem that we want to investigate. So the next step is, how could we solve this problem? First, exists such stealthy or such attack strategy, and how can we synthesize this attack strategy? And in order to solve this problem, we will leverage the field of graph games, and more specifically, two-player games. And as the name says, we have two players that in our scenario, they represent the entities of our problem. So player one represents the supervisor, and player two is going to represent the plant plus the attacker. So we can think of player two representing the environment. And this two-player game will simulate the supervisory control framework under attack. And in order to simulate, the players will have access to the current state of the plant and the current state of the supervisor. So that's the information that the players have. And in each state each state of the players, they are going to take a decision. So for example, player one is going to take a control decision since it is the supervisor state. And this decision is going to be based on the current state of the supervisor. And player two is going to take a decision that is related to the plant events or related to attack actions. And we can construct the game graph by exploring all possible actions of each of these players. And we know that this structure is going to have finitely many states because both the plant and the supervisor have finitely many states. But we can stop exploring the options for a few states earlier. And that's when we reach a critical state. So the plant is going to reach a critical state, or the attacker gets detected. So once we have this structure here, so we construct this graph game, then we can analyze it. And by analyze it, I mean that we can see what caused the detection for the attacker. And this cause of detection is going to be related to an attack action that is actually, not stealthy. So what caused this detection state here was this action that is not stealthy because the attacker is going to be detected. And what we do now, our idea is to remove these non-stealthy attack strategies so that we have a structure where every attack action within the structure is going to be stealthy. So it does not lead the attacker to be detected. And this is the idea that we have it here. So now in the yellow, in the shaded area, we have the stealthy arena where every attack action, it is stealthy within this arena. And this can be done by using the supremo controllable sublanguage. So this pruning here. And here supremo is because we're trying to find the largest stealthy arena. Now, our result is quite intuitive from this stealthy arena. It says that if there is a critical state within this stealthy arena, that means that we have a stealthy attack strategy. And this is an if and only if condition. So there exists a stealthy attack strategy if and only if there exists a critical state in the stealthy arena. So this is the first result that we present. So this is the existence result. So now we know to answer the question if there is a stealthy attack strategy that solves our problem. So I'll briefly show the game for our intersection example. So just note that there are 2 detection states and 1 critical state. And these detection states are, the cause of them is related to these deletion events at this point. So if we prune them away, this will be our stealthy arena. Now, unfortunately, the critical states are not present in the stealthy arena. So therefore, no stealthy strategy exists for this example. And I say unfortunately because here we're looking into the attacker's perspective.
Quick question.
Yeah, go ahead.
May I? Yeah, I was just going to ask. So this would be an example of a good system, right? From a defensive point of view?
Yes, from a defensive point of view, yes, that would be an example of a good system, meaning that even though there is a chance of reaching a critical state, the attacker might be detected. So it is good in this point of there's no stealthy, meaning that the attacker, there is a risk for the attacker of trying to deploy or employ a strategy and be caught. But there's still some risks because there is a critical state that could be reached, but just the attacker might be caught if it tries this attack strategy. But yeah, that's
a
true.
general question. So going back to your previous graph where you have the pruning, would you say that's, yeah, that's right. Would you say this should be a general goal in designing a robust system, resilient system?
That could be one goal if you're not worried about having, like saying that there is some risk, I'm allowing maybe too much, but the risk is kind of compensated by, well, there's also a chance that the attacker is going to be caught. If you want to be more constrained, then that's the second part. We're actually more constrained in this scenario where we don't want any risk at all. So then this system would not be a good example of a safe system, let's say, in that more constrained view.
Okay, thanks.
Yeah, no problem. Thank you. Thank you for the question. This is a good question. All right, so moving on, I said that I wanted to also introduce some constraints for the attacker. So restrain maybe the attacker a little bit more into the attacker strategies that we're trying to synthesize. And we can do that by introducing logical constraints for the attacker. So we can say that we're searching only for deterministic attack strategies or bounded attack strategies. And I have here as well interruptible attack strategies. This idea of interruptibility, it means that the attacker might be interrupted by the system. So kind of linked to the question that Nejime made at the beginning. So the attacker might be interrupted in the middle of an insertion. So in this idea of interruptibility says that the attacker needs to have backup plans for those cases. So we also have, so we can introduce these constraints in our problem formulation and solution methodology by customizing the construction and the pruning of the game arena or the graph game. And I only talked about our results related to existence, but the synthesis part now we can do by extracting attack strategies that are based on paths to the critical state in the stealthy arena. So that's how we deal with the synthesis part. All right, so there are a few other problem variations that I want to mention that we also studied before I move on to the second part. So the first problem variation that we investigate is actually, I presented here just the full observation case, but our results also are general enough for the partial observation case. And we also investigate this problem in the what I call stochastic attack synthesis, where we have stochastic information about the plant. And now we're trying to answer questions, or one of the problems that we have investigated is now we want to synthesize an attacker with the highest chance to damage the plant. So not only reaching the critical state is not enough, but we're trying to synthesize this attacker with the highest chance based on this probabilistic information. And it was in this scenario that we investigated the temperature control example I showed in the beginning of my talk. So this example was presented in the paper by Liu in 2013. And we have a thermostat hybrid system with 4 modes. And here the variable X represents the room temperature, the variable Y represents the heater temperature. The controller decides when to change the modes from this between these 4 modes. And the dynamics of each mode is defined by differential equations here. So the controller is designed to maintain these 2 temperatures within the red square. So within this region here in the red square. And the way that they synthesize this controller is that they discretize the system, or sorry, they find a discrete transition system for this hybrid system. And what we did was we enhanced this discretization, or this discrete transition system, with probabilistic information. And then we can synthesize an attacker that can reach the, can go outside of the red square with probability 1. And it's quite intuitive here what this attacker is doing is replacing readings from that are in region 4 by readings that are in region 5. And it waits until the system is in the cooling mode. So once the system is in the cooling mode and in region 4, the attacker starts to deploy this attack. And then it can do so that it reaches the region 7 here outside of the red square. So here's the simulation again, where the attacker is going to start around 1300 seconds. And we see that at the end that the heater temperature suddenly drops below 20 degrees. So, all right, so that was it for the offense side. So this is everything that I wanted to show today related to the offense. Before I move on, is there any question for this part? And then I can answer it and go to the defense part now.
Maybe I can ask another quick clarification question.
Yeah.
Partial information in your setting is just partially observing events, but you still know the model, right?
Correct. Yes. Partial. Yes. Correct.
Okay.
That's exactly what we do.
And is there a way to, maybe this is deviating a little bit, but is there a way to model not knowing part of the model as an unobservable event?
Right. That's a good question. Not that I know, and I think one of the future works that I want to explore is having partial information about the model, but I don't see a way of introducing this partial information based on unobservable events. Maybe what we can have is that the attacker might not observe everything that is observable for the supervisor, and this is a other variation. But partial information about the plant mixing with partial information about the events that I don't have any insight on how to mix those 2 problems. Yeah.
Okay, thanks.
Yeah, thank you. All right, so now let's move on to the defense side, where we are going to focus on the supervisor synthesis problem. Namely, now we want to synthesize a supervisor that is robust against the attacker. So as usual, we need to say what our assumptions are. So we We assume that the supervisor knows the plant model and as well knows the attack model. And at this point, you might think, well, this is a strong assumption, right? How could the attacker know what the attacker is going to do? Like how the supervisor knows what the attacker is going to do next. But we don't see it this way because if we recall it, we have this all-out attack strategy that is going to be encompassing or is going to represent that the attacker can do everything that is possible in this plan. So if we do not have any information about the attacker, then we can use this all-out attack strategy. And this all-out attack strategy is going to be suffice since every attack action is going to be present here. But if we have some prior knowledge, we can use it as well. And for example, if we know that the attacker only follows bounded attack strategy, so maybe we have some information about the plant and how the plant reacts so that we can use this information. Or if the attacker can only do replacement, we can also use that information. And so the attacker here is a parameter of our problem formulation. And there are other researchers that investigate this problem, but again, they focus specifically in one or two attack strategies. So either synthesizing robust supervisor against bounded or replacement attacks.
I have a question on this model.
Sure.
So is the attacker assumed to be aware of the supervisor that is eventually results?
That's a good question. Yeah. Sorry, go ahead.
Is it an adaptive attacker?
No. So the attacker here, we can use that information as well. So first, the way that we state the problem formulation, the attacker does not know the supervisor model here, as we stated. But we could have a adaptively way of using this information. So saying that, well, the attacker knows what is the supervisor model. What would introduce here is an iterative process, which would be, well, we synthesize a supervisor for, let's say, a given set of attack strategies. And then we say that the attacker now knows this model. Then if there's still some strings that, if there's still some unsafety, then we can refine our supervisor again in this iterative manner. But we do not think, the way that we pose the problem, we think that the attacker does not know the supervisor model, but we could explore this, this framework in this iterative manner to kind of have this adaptive role for the attacker. So this is actually not something, it's something that already happens in a similar problem, in opacity problem for discrete event systems, where you have this iteration where the attacker is assumed to know what is the supervisor that is going to be employed and can adapt over. So, but that's a good question. We do not investigate that specifically.
Okay, the other question is that I'm wondering whether either of these attack models is the right model in practice. Like,
Right.
I mean, this is a good starting point, first of all, but whether there could be a more sophisticated attack strategy, which is not bound. I mean, it depends on how you define bounds, but bound could be based on achieving a certain objective rather than, like, I mean, for example, you could, an all-out attack strategy could simply make events completely unobservable or make it Byzantine. For example, replacing events it's allowed to modify, just introduce a lot of random junk into the stream or delete stuff. And that would probably cause a disruption in most cases at that point, but also be noticeable probably in that sense, right? So, so the attacker strategy could be to achieve a certain objective and within possibly some constraints. And so it's more targeted to achieve a certain objective rather than just disrupt or crash the plant. So I don't know, is that something that's outside the attack model right now, or is it something within your prior knowledge model?
So it is, you can introduce that because here we're general enough in saying, well, give me an attack model, and then this will be in our problem formulation. How we get this attack model, that's a different question that we did not try to answer.
But it may be beyond a finite state machine in general. Like that's, like, are there limits on what the computability of a sophisticated attacker is?
No. So because, as you said, like for example, if as you said, like the all-out attack strategy, even though introduce a lot of junk, and it might be, it comprises every other attack strategy that we can come up with. So any other information that we have will be embedded in the all-out attack strategy. But so
that may be, I mean, it may be,
it might be too
indefensible, that strategy, right? So you need something sort of finer tuning on that, like in terms of what the attacker's capability are.
So then the attack model with some prior knowledge, and here will be given as an automaton. This is also general enough that we can comprise different attack strategies, because the way that we portray is in the general manner is the attacker has will be able to see its own edits and what happens before in order to maybe deploy some or employ some strategy. So we have this kind of general formulation of our attack strategy that is embedded in this automaton. There is some limitation here. That is, since we are dealing with an automaton, we are limited for attack strategies that are regular, that are described by a regular language.
Expressions. Okay. Yeah, that's what I was trying to get at.
But
so non-automata, or something that can't be expressed using a finite state automata, you would have trouble with.
Right. Yeah. Correct.
Okay.
That's correct.
Got it. Okay, that's fine. Great. Thanks.
Thank you. All right. So the objective here of our problem formulation is quite straightforward now, is that we want to design a supervisor that there is a clear separation between the yellow region and the unsafe region. So that means that the plant never executes unsafe behavior. So we can formalize by this constraint where we see that there will no string in the executed by the plant language reach the critical state. And again, like we want to synthesize this supervisor RA given GA and the attacker model. So this is a problem that we're investigating. And if you note, there is quite a similarity between our problem, this robust supervisor synthesis problem that we posed, and the standard supervisory control theory. And that's actually our idea for the solution approach. We were going to try to reduce the problem that we are investigating to the supervisory control problem. So just to recall you all, what we have is that we have a plant where there is a set of critical states, the controllable and uncontrollable events, and the observable and unobservable events. And we're trying to synthesize a supervisor such that it never reached the critical state and respect these constraints based on the set of events. Now, if we go to our problem, we have GA parallel A is our plant. We do have critical states in this plant. But what about the controllable events and the observable events? We need to be able to define those in order to reduce. And in fact, we cannot reduce our problem to a supervisory control problems with the current encoding format, because with this current encoding format, the insertions are neither observable nor unobservable, and insertion and deletions are neither controllable nor uncontrollable. But since this is a problem of just the encoding format, could we change it so that we can actually reduce now to the supervisory control problem? And the answer here is yes. Otherwise, I wouldn't be asking this question, right? So we need to start fixing this or changing our encoding in a manner that we're not going to change the behavior that is generated. But we have a clear way to define the the observable and unobservable events. So we first go into fixing this problem. And if we recall it, the deletions in the plans are seen by the supervisor as the empty string. And this is fine, so we can define it as an unobservable event. But the insertions, they are seen by the supervisor as the legitimate events. And this is the problem. So we need to change the encoding for the insertions. So this is our old encoding where we have the insertions as a self loop. Now we can change this by this new encoding where we will need additional states, but now we can actually say that the insertions are also unobservable, seen by the supervisor as the empty string. And now we have a way to define for our plant what are the observable and the unobservable events. So the first step is done. So we can now for our plants define the unobservable events and observable events. So the next step is fixing the controllable and uncontrollable events. And unfortunately here, we're not going to be able to define exactly what are these event sets, but we can come close and this will be sufficient. So instead of defining controllable and uncontrollable, we see that our supervisor follows a control pattern. So when a legitimate event that is compromised is enabled, then the insertion and deletion are enabled at the same time. When the legitimate event is disabled, then again, the insertion and deletion are disabled. So what we have here, instead of controllable and uncontrollable events, we're going to have that the supervisor needs to follow this control pattern constraint that we can formally define in this manner. So this is going to be the restriction that we have for the supervisor instead of the controllable and uncontrollable events. And this suffices because this problem has already been investigated in the supervisory control literature, and this is known as the supervisory control with arbitrary control pattern, so the SCAP. So it was first investigated by Golazowski and Ramage in '87, and then Takai in 2000 came up with sufficient and necessary conditions for the existence of a solution. And then we were able to modify a standard supervisory control theory algorithm to in order to have a synthesis algorithm for this problem, so that satisfied the control patterns. So our result now here is again quite intuitive. We can reduce the robust supervisor synthesis problem to the SCAP problem. And this gives us ways of knowing when there exists a supervisor by leveraging previously results from the literature. And we also have ways of synthesizing supervisors as well. So if we go back to the intersection example, now I synthesized two robust supervisors for this example. And these two supervisors, they have they're going to define a different control language that intuitively we can think as if they introduce traffic signals into the intersection, where in the first supervisor, car 1, the blue car, is going to have priority over car 2. So it's going to have the green light, and then car 2 will need to wait in order to cross. So car 2 can only cross after car 1 cross. And the supervisor 2 here will flip this priority order. So now the red car has the priority over the blue car. And this is, I think, related to the question that Ming-Young posed, like asking in the beginning if that supervisor that we had that was more general than this one, if it was safe. So it was not safe with respect to the conditions that we're investigating here. So here we're not allowing, there's no chance that the plant will reach the critical state. So that supervisor was fine in the sense that there will be no attacker that is stealthy, but there's still a chance of reaching the critical state, and we can eliminate that chance by having this with these two supervisors.
On that note, thanks for going back. Another quick question. So ensuring that there's no way to reach critical state, that's much more general about the safety behavior of the system, right?
Correct. Mm-hmm.
That goes beyond whether you're under attack or not. That just, right?
Correct. Yeah, it is, and that's one of the reasons as well that why we can reduce our problem to a standard supervisory control problem, right? Because there in the standard supervisory control problem, we are only searching, we're only trying to satisfy safety, right? So that's a good analysis as well, and connecting. But you're correct.
Thanks.
Okay, so because there is this idea, supervisors that we're synthesizing here are not unique, we decided to investigate a different solution methodology, and where we are going to have more leverage in how to extract these supervisors. And this methodology is based on graph games again. And our result is that we can find a structure where all robust supervisors are going to be embedded. And then from this structure, we can extract in a flexible manner the supervisors. And that's where we investigated the last example that I presented in the beginning of my talk, where it was a robot in a grid. We have here the robot needs to go from Q0 to Q1 and from Q1 to Q0. And the region in gray is where the attacker could modify the sensor readings. So we can synthesize a robust supervisor that guarantees that the robot is not going to crash into the red obstacles. And it's quite intuitive what the supervisor does here. It creates these two corridors where it takes the robot from Q0 to Q1, and it takes from the robot from Q1 to Q0. And namely what it does is it aligns the robot before it enters this unreliable, or where the attacker can modify the readings, and kind of it goes straight along until you reach the another safety part. And then it does the same for the corridor to come back to Q0. All right, so that was all the parts that I wanted to talk. So I went over the 3 parts that I wanted to talk today. So is there any question related to this last part or even before I move to my concluding remarks? All right, I think I can move on then. So before I go to my concluding remarks, I want to first thank my advisor, Stéphane Lafortune, and the committee members as well for the insight and questions and the comments that they have provided, as well my collaborators and the groups that I interacted during my PhD. So the UMDS lab here at the University of Michigan, the SUMO lab at INRIA, and the Queen's DES lab and Queen's University. And as well, I want to say that I appreciate all the support from my family, my partner, and our dog, and my friends. And I know that not everyone is here in these pictures. We shared a lot of good moments, but there was also some sad ones. So Brazil lost against Belgium here in the World Cup. I was not really, it was not a great day anyways. So thank you all. All right, so to conclude my talk, I investigated cybersecurity with systems model as discrete event systems, and we have investigated sensor deception attacks from both perspectives, the attacker and defender. And we use graph games techniques to blend it with supervisory control theory. In future work, we want to investigate case studies in CPS and cyber control systems as well. Relax some of the assumptions. A few, it was good suggestions, for example, that Atul has suggested today as well, that we can investigate it. And as well, investigating a little bit more the stochastics in the stochastic system scenario. So here are a few of the selected papers that are related to my dissertation and the references in my talk. All right, with that, I say thank you, and I'll be answering any questions now.
Okay, well, thank you, Romulo. Let's, whoever is not
Virtual clap.
unmuted to give a hand.